In addition to Mars, there are other locations in the solar system that are potentially habitable environments and that we want to search for evidence of past or present life. These are all more harder to get to than Mars because they're further away, and they're also less Earth-like environments. So whereas the importance of Mars is that early Mars seems to have been like the early Earth, these other locations have never been like the early Earth. But nevertheless, they may still be potentially habitable places, and so from an astrobiology point of view, we have to explore them. So after Mars, probably the next most habitable places in the solar system are the icy moons of the giant planets. This photograph shows the southern hemisphere of Jupiter. The great red spot is visible here in the background. And the photograph also shows two of Jupiter's four large moons. On the left here we have Io, which is probably not of great interest to astrobiology, but is of great interest to geologists because it's one of the most volcanically active planetary bodies known in the solar system. But the other moon in this photograph, over on the right, this is Europa. Now Jupiter's moon Europa is about the same size as the Earth's moon. But unlike the Earth's moon, it is covered in an icy surface. It has an icy crust. And yet the density of Europa is comparable to the density of the Earth's moon. So although Europa has an icy crust, it's not made of ice. It's made mostly of rock, but with a lot of frozen water on the surface. And over the years, it's become increasingly, the circumstantial evidence has been building, so it's now very persuasive, that underneath an icy crust on Europa, and before you get down to a rocky mantle, there is probably an ocean of liquid water, perhaps 100 kilometres thick. So underneath this icy moon, it's got an icy surface, but underneath the icy crust is probably a few to perhaps 20 kilometres thick. Then our understanding is there's probably an ocean of liquid water, perhaps 100 kilometres thick, and then the rest of the moon, about 1,500 kilometres worth of rock. But this means that Europa, if this interpretation of this, if a sub-ice ocean is correct, it means that Europa and other icy moons in the similar icy moons in the outer solar system probably have these huge volumes of liquid water. So that is at least one. When we talked about in an earlier mini lecture, we talked about what life requires. And I said that life requires a liquid medium, and on the Earth this is liquid water. At least one of those requirements is probably met in the interiors of these icy moons in the outer solar system. Not just Europa, but Jupiter's three remaining large satellites, Ganymede and Callisto, and also Saturn's moons Titan and Enceladus, and probably many other icy places in the outer solar system, maybe even the dwarf planet Pluto, are now thought to have these subsurface oceans of liquid water. So these could be habitable environments if, in addition to the liquid water, we could also find sources of energy and sources of organic materials, because those are the three prerequisites that we think life needs. And as we've thought more and more about these icy moons, the more it looks that at least some of them probably do have all three of these basic requirements for life, and therefore may well be habitable environments. So this slide shows on the left a close-up view of the icy, rather dirty icy surface of Europa, and then on the right an artist's drawing of what the interior of Europa is thought to look like. So here we see the hypothesized subsurface ocean underneath the icy crust. But notice the subsurface ocean is in contact with a silicate rocky mantle. And this is exactly the kind of environments where we expect hydrothermal vents to form. So bear in mind that the next moon closest to Jupiter from Europa is Io, and Io is known to be volcanically active. And it's volcanically active because its interior is pulled and stretched constantly by Jupiter's gravity. This is called tidal heating. Now, Europa is the next moon out, so the interior of Europa will also be tidally heated. Not as much as Io, because it's further from Jupiter, but there's still Europa probably still has a pretty warm, rocky mantle due to tidal heating from Jupiter. And yet, unlike Io, it's covered in an ocean of liquid water. So this is exactly where we would expect liquid water to percolate through into hot mantle rocks and be expelled to produce hydrothermal activity, like the hydrothermal vents, the black smokers we see on the Earth. And life does exist in those environments, and these black smokers produce sources of energy because they produce sources of geochemical energy from the molecules formed from the interaction of hot water with the rocky mantle. So hydrogen, hydrogen sulfide, methane. These molecules can act as energy sources for biology. They do for life in hydrothermal vents on the Earth, and so they might for hypothetical hydrothermal vents on Europa as well. So these would be really interesting to explore the surfaces of these icy moons, especially the subsurface of Europa, to see whether hydrothermal vents are present or not and whether they support life or not. But clearly they will be very inaccessible. You'd have to get a spacecraft all the way out to Jupiter, so that's 3 times further than Mars, just in distance. But then you've got to get through a kilometres thick, maybe tens of kilometres icy shell. And if there are hydrothermal vents, they'll be at the bottom of an ocean, perhaps 100 kilometres deep. So we're a long way from being able to access these oceans in the outer solar system. But nevertheless, we have to bear in mind that they probably, well, I think we can say they are potentially habitable environments. What we just don't know is whether any life has evolved to inhabit them or not. I just move on to the next slide, which shows 2 more moons in the outer solar system. On the left, we've got an image of Saturn's small moon Enceladus, and on the right, Saturn's largest moon, Titan. I'll talk about Enceladus first, because one of the key discoveries made by the NASA's Cassini spacecraft when it got to the Saturn system in 2003, it discovered that the moon Enceladus is actually venting water out into space. Now the picture on the left here shows it's a dark circle because it's the night hemisphere of Enceladus. So the sun is behind Enceladus in this image. But if you look down here at bottom right of this picture, you can see stuff squirting out, these jets of material squirting out from what is actually the south pole of Enceladus. And it turns out these are crystals of water ice. So Enceladus is venting water into space. This implies there's a source of water below the icy surface of Enceladus, probably a subsurface ocean. And so, in a sense, the evidence for a subsurface ocean in Enceladus is stronger than the evidence for a subsurface ocean in Europa, because in Enceladus's case, we can actually see the water venting into space. So again, there's a subsurface ocean here. It's potentially inhabitable. We don't know whether life has evolved to inhabit it or not. But we could imagine a future space mission to sample these plumes of water vapor and ice crystals being erupted from the south polar region of Enceladus, and studying the composition of these plumes to see whether there's any evidence for life living in the subsurface of Enceladus. In a sense, although Saturn is twice as far away from the Sun as Jupiter, so more difficult and more time-consuming to get to, because nature is naturally venting the contents of this subsurface ocean into space at Enceladus, and as far as we know, Europa isn't, sampling this material might be the easiest way for us to sample the composition of subsurface oceans in the outer solar system. The image on the right, Titan, long been of interest to astrobiologists for multiple reasons. Perhaps the first thing to say about Titan is, if you look at this picture of Titan here, it's all this yellow ball lacking in any sort of detail. And this is because Titan is the only moon in the solar system that has its own atmosphere of any significance. And this atmosphere is a significant atmosphere. The atmospheric pressure on the surface of Titan is 1.5 bars, so 1.5 Earth atmospheres at sea level. And it's composed mostly of molecular nitrogen, That's also quite interesting because the only other planet in the solar system with a dominantly nitrogen atmosphere is the Earth, of course. But whereas the Earth's the next most abundant molecule in the atmosphere of the Earth is oxygen, thanks to photosynthesis. Life has done that. The next most abundant molecule in the atmosphere of Titan is methane. But it turns out that methane, breaking down under ultraviolet light, has made this organic haze, this yellow haze, produced by the photolysis of methane in the atmosphere of Titan, which means we cannot see the surface. It's all covered in this methane smog. But the real significance of this methane smog is that it's kind of a natural. I'm going to use a piece of jargon and then I'll explain it. I'm going to describe it as a natural Miller-Urey experiment. Now, this is a reference to an experiment that Stanley Miller and Harold Urey did at the University of Chicago in the 1950s, where when they were trying to understand how life might have originated on the early Earth, they took compounds like methane, ammonia, water vapor, and sparked electrical sparks through them to simulate lightning. And they wanted to know whether these reactions produced organic molecules, and they did. These experiments produced a yellow gunge that turned out to be rich in amino acids and sugars and other biologically important molecules. Now here in Titan, we've almost got a natural Miller-Urey experiment where you've got an atmosphere with which contains methane and maybe other molecules as well. Trace amounts of ammonia and hydrogen perhaps. The energy source is not lightning, though, it's ultraviolet light from the sun, but it looks like ultraviolet light is driving these chemical reactions in the atmosphere of Titan that are not dissimilar from the kind of production of organic molecules that happens in Miller-Urey experiments when we conduct them on the Earth. So it's this yellow smog could be rich in organic molecules, and so if we were interested in the understanding the conditions in which organic molecules are produced in planetary atmospheres through natural processes before life evolves, but which life can later make use of, the photochemistry of Titan's atmosphere becomes an important place to understand.